VMAP brings the advantages of vibration engineering into the new product design cycle by enabling the engineers to quickly correlate the analyses and test results, and thereby updating the analysis models. VMAP provides a unique platform to bring the analysis and test domains together to complete the design cycle. The key applications of VMAP are vibration measurement, FFT analysis, condition monitoring, modal testing, damping estimation, finite element versus test correlation, and finite element model updating. In short, VMAP is a versatile one-stop solution for performing vibration studies and using them in solving engineering design problems. Talking about the features of VMAP. VMAP has an inbuilt geometry creation module which lets the user construct a 2D or 3D geometry to get started with the modal testing. Additionally, the user can also import solid models or meshed finite element models to get a better visualization during testing. Any vibration measurement procedure involves the hardware components such as sensors, actuators, and data acquisition systems. VMAP connects to any generic data acquisition unit, which in turn talks to the sensors and actuators and communicates their responses back to VMAP. The open hardware architecture of VMAP enables it to do simultaneous measurement through multiple channels in addition to making it portable to operate. The measurement data primarily consists of time response signals collected from the sensors and actuators. These time signals are converted to frequency domain to obtain the FFTs and frequency response functions. Any measurement is often repeated a few times to check repeatability. VMAP lets the user to preview the time signals and subsequently computed frequency response functions from several perspectives to get a complete understanding of the test process. The commonly used modal analysis approach is input-output modal analysis, which needs an excitation from an impact hammer or a shaker. VMAP supports both hammer and shaker testing and lets the user perform single input, multiple output, or multiple input, multiple output modal analysis. Another form of modal analysis is known as operational modal analysis, which is useful in doing modal analysis of large structures or in cases where controlled excitation cannot be given to the structure. One example of an application where operational modal analysis is essential is large civil structures such as dams, bridges, and buildings. In a nutshell, the user can choose the type of testing depending on the application, hardware availability, test conditions, and other constraints. Damping estimation is an important outcome of modal testing. The test data is fit to known forms of mathematical models to get an accurate estimation of natural frequencies, damping coefficients, and mode shapes. A variety of curve fitting techniques present in VMAP include circle fitting, least squares complex exponential fitting, rational function polynomial fitting, and nonlinear least squares fitting. These curve fitting procedures are used to get accurate estimates of natural frequencies, damping coefficients, and mode shapes. The correlation studies begin with importing the finite element analysis results from one of the finite element analysis software packages, followed by importing the test data measured using VMAP. This is followed by visually comparing the mode shapes obtained from the finite element analysis and test. The visual correlation makes it easy to establish the correct order of modal frequencies. VMAP takes this study a step further by computing the modal assurance criteria, popularly known as MAC, which gives a numerical comparison between the FEA and test results. After the correlation studies between finite element analysis and test are completed, the finite element model is updated with damping estimates obtained from the curve fitting process. VMAP lets the user update the finite element model with the damping estimates of various types, including material damping, structural damping, proportional damping, and multi-mode damping, based on the application. Visualization is an area where VMAP stands out. VMAP does not restrict the visualization of the modal test results to the points of measurement. The visualization technology in VMAP enables the user to get a complete picture of the vibration patterns of the test, FEA mode shapes, and operating deflection shapes of the component. This makes it easy to visually compare the results between the finite element analysis and test. VMAP is compatible with a host of industry-standard file formats and popular engineering software products. Any solid model can be imported into VMAP as an STL file. The meshed finite element analysis models and finite element analysis results can be imported from the popular finite element analysis software packages, pre- and post-processing packages, including ANSYS, Abacus or Simulia, HyperWorks, and VMAP. On the test side, in addition to the native VMAP formats, VMAP also enables the user to import any modal test data in the industry standard Universal File Format, UFF, for further analysis. VMAP provides all the advanced features and functionalities needed to perform vibration testing, but there is always a need for customization. This need is addressed by VMAP's interface to Scilab. Thanks to the seamlessly integrated architecture with Scilab, users can now get more information out of the test data using VMAP by writing their own programs. Setting up batch processes to analyze tons of test data and new curve-fitting algorithms are only two of the many ways in which VMAP's customers take advantage of this revolutionary interface with Scilab. The VMAP Scilab interface provides speed, flexibility, and infinite scalability. VMAP supports a host of finite element analysis packages. The interface between VMAP and the finite element software packages makes it easy to import FEA data for correlation studies and export updated FEA models to the respective software packages for further analysis. The open hardware architecture of VMAP makes it easy to work with several data acquisition systems. By considering the synergies between VMAP and vibration test hardware, TechPassion, through its successful Hardware Integration Partner Program, works with hardware manufacturers. We constantly update and provide the latest and most exhaustive set of supported drivers. There are several situations in vibration testing where it is impossible to place a sensor and conduct vibration measurements. Some examples of this, where we need a technology beyond conventional contact-based vibration measurements, are rotating machinery and MEMS devices. VMAP can be used for analysis of non-contact vibration data obtained using laser vibrometers. VMAP bridges the gap between virtual prototyping and prototype testing by establishing a platform to bring the best of both worlds and work on them to achieving rewards in the new product development. Some of the key benefits of VMAP are utilizing the advantages of experimental modal testing, closing the design loop by integrating the test results in the design process, and gain confidence in the FEA design through correlation studies. VMAP has several applications in industries like automotive, aerospace, energy, and heavy equipment. A typical customer uses VMAP for health monitoring, defect detection, analytical model validation, acoustic studies, and for many other innovative applications.